Physics. Hello! Hello, Lara. Long time.
Yeah.
How's your trip?
Good.
Enjoyed it?
Yeah.
Okay. Where'd you go? Korea?
I went to like Seoul and
Okay.
Incheon.
Incheon? Songdo?
Yeah.
Oh. Songdo is a nice place too. There's a big shopping sale there. In once.
Yeah.
Yeah. Did you go there?
Yeah.
Oh,
Some.
Yeah. Good. Was it cold?
Yeah.
Minus 14. I don't know how you survived it. It's gonna be really hot today.
Yeah.
And tomorrow, 39, going up to that. So, all right. Did you have a chance to look at the other videos? Okay.
Yeah.
I'm assuming that you have lots of questions.
Yeah.
It's like leaving there. Oh, question mark, question mark. So, what I'm going to do, we're going to revising some, and then go through some of the questions together too. Until we kind of master or like understanding the contents, I'm not going to give you a test. Don't worry. Yeah, but we have a test for chemistry.
Oh,
Yeah,
okay.
chemistry, that test you missed, you need to organize a day to come back with the test
Oh,
again
yeah.
too, because we are finishing off the module 1 this week,
Mhm.
and then next week we're gonna have module test. So
Okay.
prior to the module 1 test, I really want you to take the test we did in the last week here. Those questions are something that I went through a lot. Hello, Yubin. You're breaky?
Yeah.
If you're really hungry, you can have that while you listen to me. That's fine, okay. Just wait for Christine, and assuming that Damien is here, just checking.
Can I have a textbook?
Oh, of course you can. Sorry. Got it ready here. Hello, Christine. Okay, everyone see now? Okay, let's start. I know. I just described. I talked to him at the. How'd you go with the homework? Okay. I just explained that what we're doing right now, forces, and what we're going to do today is it's like a huddle. I really say this is a huddle. Like, people like just kind of go over the hurdles. They just kind of fail, and then they drop out the physics after this. And you probably know why from that what we did last week, like cosine, sine rules, kind of like flooding of those. So let's do it. Before we go through the some homeworks, then actually I will. This is for you. Let's revise that what we have up to two. So from the beginning of the this year, we learned about the vector sum. Okay, so vectors are, we have, like we talked about in module 1, velocity, acceleration, or the displacement, all that. So simple rule for the vector sum is that the head to tail, then tail to head. You remember, so when we have two vectors, okay, make a, if you want to find the sum of those two, so V1, V2, for example, this is V2 plus V1. They're adding the head to tail of the two vectors, then tail to head of that. Okay. In other words, when we have a diagonal vectors, say V1, V here like that, we can also analyze the vector as we have horizontal vector x and vertical vector Vy like that, which is making the right angle triangle. Okay, and with a certain angle, of course, the theta over here. This is the first rule that you have to remember for the vector sum. And the last week, we kind of move on to the module 2, that we kind of finish all the relative velocity. Do you remember all the relative velocity? We have many examples. Two cars joining, seeing each other. You can find the relative velocity. There was one type of questions, boat question, and they're going to the river. So I get a push by the river too. So, like a relative velocity. Just writing here, VA to B is known to be VA minus VB. And just remember that the negative vector equals to the opposite direction. Okay, direction. So if this V, that means this is minus V of that. Okay. Now, after we kind of mastered those, like in the sum vector sum, we started learning about forces. Finally, we jump into what the forces are. Do you remember what the force is, Matthew? Like I gave you a definition of force, and I asked you not to use F equals to ma. I mean, we're gonna use that by the way, but how we define the force?
An interaction, changes in motions, changes in scale of motion.
Changes in motion. So whenever we get the forces, it changes the motion of an object that carries the mass. In other words, in the presence of the force, you will get the change in motion. And have a think about what I mean by change in motion as well too. When I say change in motion, we kind of discussed that in the module 1. Whenever you have a change in motions, we describe that as there is an acceleration applied. And I describe the acceleration, kind of different concept, different definitions from an everyday use. It's not just a change in getting faster. It's all about the change in velocity. Okay, so change in velocity as in we have a change in the direction, change in the magnitude. So all of those are kind of including the change in motion or acceleration there too. And this is why we can use F equals to ma later on. All right, today we're going to talk more about F equals to ma a bit later. But before we move on to that, we also learn about something known as static equilibrium. Last week, this is something we started, okay? Yumin, what does it mean by static equilibrium?
The net force is zero.
Okay, it means the net force equals to 0. Okay, now what does it mean by we have 0 net force in terms of the motion? You're thinking about the definition of force here. I just described that as in the presence of the force, we have the change in motion. Okay, means that if you have a 0 force, there will be no change in motion. This is represented as there's no change motion. Now, what's meant by no change in motion? We only have two situations that we're having no change. One is when you're in stationary, when you're not moving at all. Okay. Another is when you're in the constant velocity. Remember this, that the net for zero situation is described as it's either be stationary or when you're moving in the constant velocity. Does it make sense? Okay, because when you're moving constant velocity, for example, like if you're constantly moving, say 10 meters per second to the left, then you wouldn't get any acceleration, and there's no force applied on you so that you are able to maintain that position or maintain the velocity. So this is purely just talk about Newton's first law. Newton's first law of the motion. You may like to remember the Newton's first law as law of the inertia, okay? But I wouldn't like to say like inertia is the everything. It started from here. If one thing is stationary, an object is stationary, unless it gets affected by any of the acceleration or affected by the forces, it will be stationary forever, okay? Which in other words, it's talking about static equilibrium situations. Now, when we're breaking the static equilibrium by applying any force, like I'm lifting this pen up, I've broken down the static equilibrium because I apply that pull of this pen up. Okay, so you see that from that nothing, like no motion, it's kind of lifted up. Or whilst you're walking like forward, okay, if the wind blows from the back and kind of push you back, okay, means you're gonna walk a little faster. That's also the breakage of the static equilibrium, which makes you run faster, or sometimes like wind blows from forward, make you run slower. Does it make sense? Okay, this is the true definition of Newton's first law. Then inertia comes with that. That inertia is that you want to maintain that. You want to keep the same motion. So you would feel like there's some sort of the resistance that you would feel like that. If I try to lift the pen, in the instant that I'm lifting the pen up, I can feel that the pen's kind of heavy. The sensation of the pen, the heaviness of the pen is, I can describe that as inertia. Okay. In other words, the heavier the object, if you think about it, I'm trying to lift it 100 kilo, it carries the greater inertia because it's hard to lift it up. Does it make sense? And it means that the object, which is 100 kilo, wants to stay in where it is. This is the law of the inertia, which is a part of the Newton's first law. So do not just define Newton's first law is the same as the law of the inertia. That's a misconception. Okay. The last week, then we kind of combined that vector sum to the forces and the static equilibrium. Do you remember that we have a picture that's hanging, or anything is a mass is hanging, say 10 kilo, is a hang like this. Okay, it's not on the floor, by the way, it's a hanged. Then we talked about if this is, first thing you need to do is you gotta determine the motion of the object you're given. Okay, Matthew, what would be the motion of the 10 kilo if it's a hang with the two wires?
It's stationary.
It's a stationary. So after you determine, this is the stationary, then you would know that, that means stationary as in like static equilibrium. You can directly come to, you can determine the net force direction. Does it make sense? Okay, that means in this case over here, the net force is 0 because it's stationary. Okay, the situation can be varied because sometimes it's kind of slightly lifted up. That means I wouldn't say it's stationary anymore, but I mean there'll be a net force applied to it. Okay, this will be like some kind of universal template that you can use. Once after you determine the net force and the net force plus the direction, the next steps you need to do is determine and then analyze all forces components. In other words, what makes the net force, the sum of the forces, to be 0? So in the case of this, for example, we have that two wires are pulling this up. So we have a tension force 1, tension force 2. Okay, so I will write that as the separate tension forces applied, and there's another force that always put this one down called a weight force. So Fg, or the weight force. Does it make sense to all? Okay. Now, once you get it up to this stage here, it means that we determine that we have the Ft1 plus Ft2 plus that Fg is all your force components that making into something known as the sum of the forces, or net force. But remember that that's a 0. We learned that. Does it make sense? Okay. Now, if you have any diagonal vectors, for diagonal vectors, or the forces, analyze their horizontal x and y components. So what I mean is we have Ft1 that's going upwards like this. Yep, so we have one diagonal vector. So as I describe that in the vector sum, or the vector rules, that we have a diagonal means it can be divided into one horizontal and one vertical, like this. So I'm gonna name that as this Ft1s, or just say T1s, because I want to say the T1's x, and there's a T1's y vector, which is in the right angle triangle like this. Okay, now same things for the Ft2. This has a horizontal and the vertical. That's a T2x and T2y. Okay, I'm just using something we learned that apply over here. The reason why I'm finding that all the horizontal and vertical component is because I can't add up these two diagonal vectors directly. So I kind of analyze that, divided that into two components so that I can add them up. Once you get up to this stage, then 5 adds up, find the sum of each components in x and y. So let's find the line here. We have the net force on x, just for the x-axis, not horizontal axis. The only force that you have on the x-axis from all of that is we have T1x and T2x. That's only for the horizontal. Now, because we kind of divide the Ft1 into that, you don't really need to count the diagonal vectors anymore, because this is a vector sum. One thing that you have to make sure is you need to concern about the direction here, that Ft1x is moving towards the left, T2x is moving to the right. So taking the left out, the negative direction, and right to the positive directions, you need to write it down as, T1x is moving to the left, T2x is moving to the right. And this gives you the net force to be 0 too. How do we know it's net force of 0 again too? On your horizontal axis, the box is not moving. So the net force on the x is also be 0 too. Does it make sense too? Okay, we can also do the same thing for Fy. In this case, we have 3 components of the y-axis. One is T1y, which is moving up. We also have T2y, which is also moving up. And do not forget that we have a weight force that applied. But this is a negative F of the G here like this. The sum of that is also be 0. Does it make sense up to here? Now, it's just simply like, okay, then we have a T1x. The problem here is that how do we find the T1x, T1y? Then this is the time that using the trigonometry. Using trigonometry to determine the x and y components. So if we know the angle that this is a theta, that's an alpha, okay, that means we are able to find that the T1y from that, let's write it again, T1y from this right angle triangle must be using the sine. It's a sine theta. And sine theta equals to the opposite of a hypotenuse. That means T1y must be ft1 times that sine theta. That's how we can use the trigonometry to get the actual value. Then T1x would be ft1 times the cos theta like this. Same method, T2y would be then ft2 is from this triangle there times that sine alpha, and T2x would be ft2 times cosine alpha like that. Does it make sense? So we're more likely given some of the angles too, and then what you do, you substitute the values here. Then instead of the T1x, you can now put it into ft cos theta. Instead of the T2x, you can put ft2 times cos theta. Does it make sense? But remember that the sum of those are the 0. Good? Then, last step, you just need to solve a simultaneous equation between two. From the x-axis and the y-axis. And this is why I described that it's really mathy. It's a mathematical approach too. Sometimes you may need to use the cosine and sine rules to find the angles or the forces from that too. But this is a kind of general, like the template of the force sum question they can apply. That it always started from that motion, determine the motion. Something that's very important because you can get some questions like, hey, it's moving, it's getting accelerating too. Then you have to catch that the net force is not 0 in that situations. We're going to talk about that in chapter 2, and once we're talking about Newton's third law. But today, let's focus more on first half of today's class. Let's focus more on some of the questions you have in your homework. Okay.
Can I get a tissue?
Yeah. Take that. Let's start. Matthew, does it make sense?
Yeah.
Yep, give you some ideas how to. So I just leave the template here. Let's use the template to solve the question today. It's okay.
Could you also cover the coefficient of friction?
Oh, the coefficient of friction. Okay. So from the many type of forces, assume that we have something in the here, say 10 kilo again. Okay. When you try to push that, you actually feel something. Not lifting. When you try to push that, because like I said, the friction force exists between the floor to the mass. You actually feel that some of the resistance. So the friction force, we have many type of friction forces, like a sliding friction force or like the static friction force. But I'm just simply talk about when it's stationary. The static friction force can be defined as amount of the normal reaction force from that R times that the mu, which is known as the coefficient friction coefficient. And this is the normal, the reaction force. Remember, the normal reaction force means it's a perpendicular to the surface. Normal means perpendicular. Perpendicular to the surface. So in that case, the perpendicular force for the surface would be, this is a normal reaction force, okay? And the weight force is applied down here like that. In the case of this situation here, because again, I'm using the static equilibrium, the box is not moving up nor down. So can we say the net force on Y is 0? Yep, because it's not moving up nor down. That means that the weight force plus the R is 0. Considering that weight force is moving negative directions, so that's a negative weight force like this, then it gives you R equals to the weight force, which is mg in that case. In the case of the when there's something perpendicular stationary in the perpendicular or the plane surface there. Now, what does a mu stands for? Mu, again, is a friction coefficient. Depends on the type of surface that you have, we can determine the different type of the coefficient value. This is more like a constant, a fixed value. The value that we can't really change it. So each of the surface would have the various coefficient values. So have a look at the example of the coefficients, page 7. It shows you that static friction coefficient, which is like friction values, get varied. The rubber on the dry concrete is 0.9. Compared to the steel on the ice, it would be 0.1. So you don't worry about memorize any of those values. You will be given the static friction coefficient values. Okay, and means that you just need to get that, because you can imagine that it's hard to pushing the rubber on the dry concrete is really hard. Okay, because due to the greater friction force. However, steels on the ice is something that very easy. They get sliding through, kind of proving that even though they have even the same mass, because of the coefficient values, the amount of force required to move that is different too. That's what I mean by friction coefficient. Does it make sense? Oh, okay. Okay, we're gonna come back to the coefficient values because we're going to do some questions related to that. Okay. We did up to this question. How did you go with the 1.5? This is actually part of your homeworks as well too. And question 1, 2, 3. Let's go through that questions together to understand more about static equilibrium. So assuming all masses in the diagram are static equilibrium, again, means that highlight that. This means net force is 0. It's not moving node up nor down, or left and right. Determine the values of the resultant forces or the force labeled F in each situation here. So let's go for the A. First of all, we have a push force there. It's in the static equilibrium. We have first, it's in the static equilibrium. Let's use a template. Determine the motion. That is known that net force is 0. So I show you a full working out for each of the questions here. You can write it down, or you can just and then you get the answer checked. Net force is 0 because it's not moving, or it's given as static equilibrium. Good. B. Are we done the 1 and 2? 3. Determine the all forces components there. So what we have here is we have a force that is hidden. The mg is also given here. We have a force that is applied. We have a tension force applied here like this. Okay, so we have 3 force components that we can say this means that F plus mg plus T is equals to 0. But the problem here is the force mg and T, they are in all different dimensions, all different directions. So what we have to do is we need to then find the, for the diagonal vectors, analyze the x and y components from here too. The only diagonal vector that we have is the tension force, the T, with the angle here, it's given at 35 degrees. Okay, means that for the diagonal vector here like this, moving to this direction, you will say, oh, moving up and so moving to right and up. So there's a Tx and Ty from now. Does it make sense? Okay. Now let's do this process of finding Tx and Ty and Tx in using the trigonometry and the right angle triangle there. Ty can be written as T cos 35 from the given triangle, and there'll be T sine 35. So I just can write down which is step 6 first of all. Before I move on to step 5, I can just mix use that. Then once you get up to this stage here, you can write it down all the force components that you have. You have F on X axis is, think about what we have on the X axis here. We only have F, and if this is going into this direction here, there's Tx and Ty like this. On the X axis, we only have F and Tx, which is moving in opposite direction. Does it make sense? Okay. But the sum of those two are known to be 0 because it's a static equilibrium again. This means Tx, which is T sine 35. Yep. Then, considering the direction of the F, which is moving to the left, I can just write as F here like this. Does it make sense, though? Okay.
If it's on the x, wouldn't it be cos 35?
for this triangle. Oh, for this triangle, it will be sine. For this triangle, yeah, it varies, by the way. It varies by the triangles too. So this is why you need to draw the vector diagram and try writing the triangles, because it's not a formula, by the way. Because I can't really tell, because I don't know like what angles will be given. All good up to here, okay? Now I can do that for Fy. That also be 0, and just showing you that the Ty will be Ty minus mg. The reason why I put the minus mg is because it's moving in downward directions. This can be rewritten as t cos 35 minus mg here like this. Does it make sense to all? Okay. I mean, I know this is a really short question. Little space given here for working out, so you might need to do this extra space. Okay. Now, from y, what we can tell is, can we say t cos 35 is equals to the mg then? From here, 1 and 2. Let's write it down. From 2. The t cos 35 is equal to mg. In other words, I can make that in the subject of t, that's mg over cos 35. Remember the purpose of the question, we want to find what the f is. To find the f, we need to know what the t is. Okay, there's no way we can find the t from the first equation, so this is why we use the second equation. Like it's exactly the same as like how you're solving simultaneous equations. Does it make sense? Okay, then t is equal to mg cos 35. You're given the m. What's the mass of this? 20 kilo. 20 times 9.8 divided by cos 35 will be given as equation 3. I just leave that for here now for the exact value. Then what you can do, you can substitute the 3 into 1, which is the first equation. That f is then equals to t sine 35. From that, that's 20 times 9.8 divided by cos 35, because that value goes into t. That times that to sine 35. Now, what is a sine divided by cos? 10. So this gives you 20 times 9.8 times 10 35 here like this. Okay, so because that is giving you the 10. Then last step, just use your calculator. So 20 times 9.8 times 1035, you will get 137.24 Newton. Or in a 3 sig fig, it will be 137 Newtons. And this is the final answer then. Takes quite a while and thinking about the questions too, but did you realize that I'm using this template, exact same amount, the same template here? Okay, so it doesn't really matter what forces you're given and what directions you're given. You got to use this kind of same method over again and again to do that question, to solve the questions. Okay. Oh, the t, sorry, I forgot to find the t. The t would be then, we can substitute the values here, 20. So t, we can use that 20 times 9.8, and cos 35 gives you 239 Newtons. So from here, from the equation 3. Okay, I know. After you completed your working out, when you're looking this like, whoa, what the hell? Okay, I didn't expect this is gonna be really this complicated, but if you think about the step by step here, it's really what I mean, like step by step. You can't just jump from here to there straight away. It needs some probability processes that's showing that the resultant vectors or force component, net forces to solving the simultaneous, and bit of like trigonometry there too. So it's looking really complicated. It looks like a mathematical questions, not a physics questions too. Yeah, I probably told you like the prerequisite for the physics is extension 1 mathematics for this reason too. You have to be really quick on the catching that. But any questions about question A? Matthew, you good? Does it explain to you why we need doing each of the processes there? Yeah. Okay. B, find the value of the F1 and F1 and F2. let's do that. That's gonna be something that's similar. Can I delete that now? Erase this, or can I do you want me to leave that for a while? No? Yeah? Okay, I'll leave that. Okay, I use this way. Can I leave that now then? Okay. Going back to here, because I leave that here, so you can just look at like what will be the next step after one and after one after. So let's do B. Define the value of F1 and F2. So let's think about it here. Again, determine the motion. It's given. It's given that it's a stationary or static equilibrium. So the net force is equals to 0. It's given. Okay, we can figure it later. This way. Okay. That means F equals to 0. That's always started from that. I know this is kind of repetitive questions. Then think about the force components there. We have F1, F2, and 48 newtons pushing it down. And this is giving you the 90 degrees between them. Does it make sense? Okay. Then we got to consider about it in here that this is going to be a little tricky. F1 and F2, adding them up. 90 degrees. Let's do it in this method. Means that when we're adding the F1, the vector, F2, vector, and 48 newtons down, this is making to be 0 all together there. Okay, now, slightly different to the first method there, because what I found here is, it's sometimes hard to find that and the force components in the given situation here like this. So what I do, rather than doing the mathematical approach, I do the vector approach here. That I'm using this, F1 plus F2. Okay, we learned that the vector sum, that when we have two vectors, if say we have two vectors, the F1 and F2, given here like this. Okay, Christine, if I ask you to add these two vectors, how would we show like adding these two? Head to tail. So F1 head goes on the tail of the F2, and tail to head, which is going like this situation here. Does it make sense? Now, what was the angle between F1 and F2? It was given as 90 degrees. Can I say this is 90 degrees then? Okay, does it prove that? Means that this is a vertical vector produced. This is known as F1 plus F2. Does it make sense? Okay, this is a second method that we can approach to these kind of force diagram questions using the vector diagram sum. Then we have F1 for the F2. From that, we have 48 newtons down here like that. Does it make sense? Up to here. Then, could we think that this is 48 newtons? So from that, as a vector sum is that, then can we say that F is a 0, that means F1 plus F2 plus minus 48 is a 0. This gives you that F1 plus F2 is then equals to 48 newtons. Simply because they're in a static equilibrium situation there. Okay, so we found the sum of the F1 and F2, which is the length of the 48 newtons there. So think that as this is a 48 newtons in terms of length. Then, as we know, there's F2 and F1 is in the right angle triangles. Are we given any other angles too? I'm assuming that this is the same length. I mean, this is the only way we can solve the question there. If this is an isosceles triangle, then you can use a trigonometry. The angle would be 45 and 45 in that case. Yep. Then you will find that F1 is then equals to, or same as F2 in that case over here. You can either use anything, so 48 sine 45 or cos 45, you get the exact same answer. In the exact value, root 2 on 2, remember that? So it'll be 24 root 2. Or you can use the calculator to find some approximate value, 24 times root 2. 24 times root 2, you get 34 newtons for each. You may do the first method too, like finding the vector components too, but in the case of that, I prefer using this. So think about the various method, or think about the vector sum of two. All right, C, find the resultant force of between two. So we have 16 newtons push it up, 18 newtons push it down. The way we can find the resultant force is always vector sum. So head to tail, then tail to head. So head of the 80 newtons go to the tail of the 60 newtons, or you can simply build like a move that a parallel line, and the resultant vector will be this. So what is this? We have a vector or the right angle triangle with the 60 and 80. So the way we can find that is use the Pythagoras. So the force would be, the resultant vector would be 60 squared plus 80 squared, and the square root of that, that is 60 squared plus 80 squared, and square root of that, you get 100 newtons for the length. Direction, find this direction here. So the angle would be 10 inverse of the 60 on 80, and 10 inverse of that, you would get 37 degrees there. So this is the final answer. It would be 100 newtons at 37 degrees above the horizontal. Make sense? 12, easy. B, find the resultant forces too. Okay, in the case of that, we have two forces. This time we have something diagonal. So again, move that migrate to the here. So you just see that it's making some sort of parallelogram. That's 120 newtons. And with the making the 40 degrees here like this. So if that's started here, the resultant vector is always the same. Head to tail, then tail to head. So head to tail, then tail to head. So this is your resultant vector now. Now we have a triangle then. This kind of triangle, which is showing the 40 degrees and 120 newtons and 160 newtons. What should we do to find the length, or to use sine and cosine rules to find the angles and the length? Cosine rules to find this, the c squared is equals to, so c squared equals to a squared, so 120 squared plus 160 squared minus 2ab, 2 times 120 times 160 times cos c, which is cos 40. And so you can find the c from that, square root of those, plus 160 squared minus 2 times 120 times 160 times cos 40, and square root of that, you're going to get 102 or 103. 103 newtons for the length. Yeah, okay. That's like a math question, by the way, rather than the physics question. Okay. Angle. So you have to find this angle over here to determine that does it evolve from the horizontal or from the verticals too. If you can take any of those. The theta can be found from using the sine rule. If you can use like cosine rules, 120. So sine theta of 120 is equals to sine 40 on 103. Therefore, theta is sine inverse of that, sine 40 divided by 103 times 120, and sine inverse of that value, you'll get 48.5 degrees. Therefore, it'll be 103 newtons at 48.5 degrees above the horizontals. Pretty doable questions up to here. Okay, when we did that, kind of back to some. I warned you that yes, I'm sorry that you get the cosine sine rules, but we had it in the HSC too. So it's got to be really similar for E and F and G and H, which is all given here like this too. So let's do the H. Okay, let's do one of the questions, the H. Let's find the resultant vectors, the forces that we have. Okay, give you about a minute to think about this question if you haven't done it. H. What if we have a 3 vectors and you need to find a vector sum of 3 vectors? I show you 2 methods for those. So yeah, I show you 2 methods. At the end, they're the same. Okay, method number 1. Oh, still going? Okay. Give you. Okay. Method number 1, as we did for question C and D, you can use the vector diagram to add it up with the vectors. So remember that some of the vector means that head to tail, tail to head. So we can draw the vector diagram to show that. So I got to do one by one. So adding up this 60 newtons at 30 degrees and 80 newtons at 30 degrees first of all. Okay. Or we can add it up some of the vectors given over here. So make sure 80 newtons to 60 newtons. So let's do that. 80 newtons, which are 30 degrees there. And head to tail, so giving you the 60 newtons going in this direction, making that in 30 degrees. Okay, and then add that to the 60 newtons head to tail again. That's 60 newtons to here like this. Okay, so it's at the end you're gonna find that head to tail, or you gotta think about it here. By adding these two, so 80 newtons, 60 newtons. Forget about 60 newtons there. You get the resultant vector that is going up like this. Does it make sense? Okay. Then what we can tell from there is this is a 30. Okay, that's a 30. Can you see that? This is actually making the right angle triangle. It will like all like the vertical vector there. Does it make sense? Okay, bit of like a trigonometry or geometry method. Then you only get this is if this is the vector 1. The green plus 60 will give you resultant vector of this vector. Can you see that? Okay, this is what? The right angle triangle vector then. This is the first method that we can use using the vector diagrams. Then the resultant vector would be that we have, this is 90 degrees, 30 degrees there to forget the sum of the vectors too, or you can use the vector diagram to solve that. Okay, so I leave that for here. This is first method. They're using the geometry method. That using that geometrical method that we can find that the right angle triangle. You just need to find the resultant vector, which is the hypotenuse over here. Does it make sense? Okay. Now, second method. Method 2. Method 2. Now this time, bit of algebraic method. What I mean in algebraic method is the one that I showed you in the template. Simple as that, okay? Starting from that, motion is the static equilibrium, so net force is 0. Okay, then once we get it up to this stage, we've got to think about the forces. So let's name the 60 newtons there, 60 newtons, 80 newtons, 60 newtons. Some of those are making 0. All right, so then we have two diagonal vectors. One is 60 newtons that's going into the 30 degrees. So it has two components, x and y. That's say x, 60 of the x and y. So for that x component it would be x1 and xy2. So differentiate that. X1 would be from this right angle triangle, x would be using the cosine, 60 cos 30. Y1 would be 60 sine 30. You can get the exact values right if you want to. Okay, in the second vector, which is 80 newtons going up, that we have a 30 degrees again, up and down. Okay, this is assume there's x2 and the y2 to differentiate that, x2 and the y2. x2 would be from this right angle triangle, 80 cos 30. The y2 would be 80 sine 30. Make sense? Okay, then you gotta think about another vector here. So let's think about the f on x, all the x components sum. We have 60 newtons that is going to the right, okay? x1 plus 60, but that's moving to the opposite direction, so negative 60 cos 30 plus x2, 80 cos 30 here like this. Same thing for the fy. Would it be what? Adding all the vertical vectors that we have. We only have y1 and y2 for the vertical vectors, so both of them going move up. So we have 60 sine 30 plus 80 sine 30. Make sense? then what do you do? Just use your calculator to find the some value because we don't have any variables there. 60 minus 60 cos 30 plus 80 cos 30, you're to get 77.32 newtons. The Fy gives you 60 sine 30 plus 80 sine 30, you're to get 70 here. Then this gives you a new vector diagram. This is the Fx, the sum of the Fx is then 77.32 newtons going into this direction here. Fy is going on to 70 newtons up. That's the same as Fy. Again, using the vector sum, head to tail, tail to head. This is a resultant vector, which is just exactly like that. Does it make sense to all? Then you can just find a use the Pythagoras. That 77.32 is actually preferred this method. It's better. 77.32 square plus 70 square, and square root of that, you get this vector of the force. Resultant force would be 104 newtons. Angle with the theta would be 10 inverse of the 70 on 77.32. So 70 divided by 77.32, 10 inverse of that, you get 42 degrees above the horizontal. So final answer, yeah, okay. Net force is therefore 104 newtons above the 42 degrees above the horizontal. At, I should say, at 42 degrees above, that's the right word, the horizontal. Again, just simply use the same method. Looks complicated, but in fact, it should be doable. Should be doable by now. Okay. Does it make sense? Okay. We can use the first method, by the way. If you have like a ruler protractor and just measuring the actual angles and the length of that, you can actually do that too in the scale diagram. But most likely, you need to use the algebraic method like this. Any questions? No? Okay. No? Okay. How'd you go with the this? Did we do that last week? Question 2. I kind of left that because I want to go through that. And you actually had that in your homework as well. Shall we do it? An unknown mass hangs from 2 strings suspended from the ceiling as shown in the diagram. Find the value of the M and T2 so that the system is in static equilibrium. All right. All righty. Adding that and that, and give you an angle of that. Okay. Let's do it. Question 2. First things you know from that system, it's a stationary, or it's giving you that static equilibrium from the question. So as soon as you hear that, you gotta find out, oh, that means net force is 0 situation here again. Net force is 0. Okay, after you get to this stage here, let's draw that vector T. So we have one vector, which is T1 at 274 newtons. And with the ceiling, it's making the 45 degrees. And we have a second vector, T2, that's making the 40 degrees. And that's hanging mass M here like this. From the mass hanged, we would see that there is the wave force, mg, or let's write that big capital MG. Capital MG is hanged. Okay, it's moving downwards too. Now what we have to realize from there is a string that hanging this mass over here. Okay, so you got to think of like we're hanging something there. Do I have a string here now? No, I don't. I will bring it later. We have something. If a string's hang, if something pushing downwards too, you will have the reaction force in the same direction. Or you would think like, oh, this is kind of transferred to this direction. This is kind of pulling this mg down here like that. Okay, that's the property of the tension force. It's a bit of like an action and reaction force applied into. So what that means is you can just use your common sense or like the imagination. If we're saying pulling something, obviously that tension force exists in the short string would be same as the mg. Okay, without the mg, it would be the stationary. We're pulling it. Does it make sense? Okay. So we have 3 type forces. Don't worry about like this one here anymore. we just got to use the mg like this. So just purely showing the vector diagram. Okay, well, it looks a bit complicated by just looking at that, but this is something that very similar to what we have done before. How do we do it? You got to think about the diagonal vectors, that it has components of T2 has component of T2x and T2y with the right angle triangle. T1 also have the two components, T1x and T1y here like this with the right angle triangle here there. Then it's a bit of like a geometry, okay. Parallel to parallel lines, we have the angles that you see that, oh, that's making a 40, that's making a 45. Okay, so we have a right angle triangle with the 40 and the 45. So that means we are able to find the T1y from that right angle triangle. That's given at 274, given that T1 sine 45, and T2y, T1x would be 274 cos 45. But if you realize that 45 90 degree means this is an isosceles triangle too, you may use that too to figure out, or same as the T1x, but that's just the value anyways. Okay, now same process for the T2y, and we don't know what the T2 is, so to leave that as T2 times that sine 40, and T2x would be T2 times cos 40 here like this. After you rearrange all the diagonal vectors into force components, write it down, then the sum of the fx's, find out all the x components that we have T1x and T2x, and that's it. We only have two. So make sure you write the correct direction of that. T2x is T2 cos 40, that's moving to the right in the positive direction. T1x is in the opposite direction, so I'm going to take that as a minus 274 cos 45. Guess what? This is 0, isn't it? Because it's a static equilibrium again. So, I think we can find the T2 from here. The T2 is therefore that 274 cos 45 divided by cos 40. Here like that. Then you would get 274 times that cos 45 divided by cos 40. Then you would get 253 newtons for the T2. Good? Okay, now time to use the y component, Fy, adding all the y components that we have. What we have now, we have T1y, let's write it down, this first, T2y, that minus the mg. Okay, y is a minus, or you can write the minus mg due to that direction. Then substitute the values, 274 sine 45 for T1x. Now T2, we found the T2 from the previous here, so we can just use that 2 plus 253 sine 40, 253, and T2 sine 40. I just simply use that, minus mg. It's given as this. Guess what? This is also 0. Because they're in a static equilibrium. Then we can just find the mg is equals to, adding these two up, 274 times sine 45 plus 253 times sine 40. You'd get 356.37 newtons. To find the m is then that 356.37 divided by g, which is 9.8. Remember the g is the constant value, like a pi, as 9.8 meters per second squared. G is not the negative 9.8. Negative always means like the opposite negative direction. Okay, so we put the minus mg, not the g, minus g. So that divided by 9.8 from the exact values, you'd get 36 units for the m. Anyone? What is m? M is the mass. So units is kilograms. Done. Okay, I know it looks really complicated, like, oh wow, we're hanging. Okay, mass is hanging. Oof, what do I do? Okay. Again, I'm using the templates. I'm using that, giving you some ideas about, oh, this is how you do it for this type of questions, or many type of questions look like this too. And not only for that, for other type of questions, you can use the same template. Just be aware of that diagonal vectors and analyzing that Common mistakes from the students, they forget about put the negative value. They forget about put the negative value here. So get the really small t there for small m values too. Make sure you put the negative value for the opposite directions. Question 3, how'd you go with this one? Kristen's like, kill me, okay? One of the hardest questions you can get. Pulley questions. You will, I'm sorry to say, you will hate pulley. You will like, oh, pulley again. Okay, give it a go. But can you try to use the same method that I explained today too? Think about the analyzing the vectors and just, let's start it from that. This is also in your workbook. I provide you some working space, extra working space from page 90 on the workbook too, so you can use the space provided rather than using the small space. Give you 2 more minutes. Okay. There's a chance the question might be faulty. All right, let's briefly talk about what the tension force is. So this is how I can represent the tension force. So you have a string that in here, okay? And from the string, you can see like it's getting straightened due to the mass of your hand over here. Now, this is showing you the static equilibrium because it's not moving up or down. So thinking about what forces that apply from here, that the weight force from the mass is kind of pulling this down. Now, the reason why it's stationary is because my hand or my finger is holding this. Okay, this means my fingers now or my arms are applying the same amount of the force from the weight. That's for it maintaining the tension force. So there are two types of tension force exist in this case. One is that this side over here is pulling this side down, okay, or from my finger, or the tension force pushing up. So tension force is a kind of example of we describing that action and reaction force in Newton's law. But what if we introduce that, put it into the pulley? Look like this. So this is a pulley, basically, showing you the similar situation there. If I put that in the pulley, then I'm holding the force like this, okay? Now, in case of the stationary position over here, you'll see that the tension force from this side here, that mass is pulling this down, the tension force is going downwards due to that mass of the pulley. But at the same time, I'm the one pushing this forward. Okay, so there are two types of forces exist. That's one is pushing down and pushing forward. Okay, so how to set this one here like this. Sounds better, okay? Which means in this kind of pulley questions, we may consider about, we have two forces applied. One is, yes, it's kind of pulling this down, so the direction of the force is, the mg is going downwards here like this. But there will be another force, a Ty, I call it tension force exerted from the y, is pushing this one up, Py, and Tx would be going up in this direction too. Therefore, they're able to even out, they're able to reach the static equilibrium. The force that is, of course, is related in here like that, okay? But this is kind of exerting the opposite force, the same as the amount of that. In other words, in terms of the magnitude of Tx, this is same as the weight force of the mass you hanged as well too. So in other words, mass of the x times the g. I just write that as xg here like this to make it simple. Does it make sense? Okay. Then Ty, the magnitude would be same method. Yg goes like that. Okay. Now you're asked to find what the x and y are. So let's do that. In a static equilibrium, we have two diagonal vectors. One is 25. So from this going into this direction, that's xg, or xg. Sorry. It has up and down. So this will be xg's x, and that's xg's y. Go like that. Or simply you can say tx of x, doesn't really matter for that. Same similar vector, we have a ty, which is, I just named that as yg's. So we have two vectors in the right angle triangles, that is yg's x and the yg's y vector. So in terms of the angle, the 25 and there's a 45. That's given in the question. Make sense? I'm doing exactly the same thing as what we've done before too. So x, g, y in here, instead of using that, using the trigonometry, xg times that, they're using the sine 25. And xg of the x would be xg times that cos 25. And yg of the x component would be yg times these cos 45, and yg, I should write it the other way, sorry, yg, let's do y first, that'll be about yg times sine 45, and ygx would be yg times cos 45 like this. Make sense to all? Okay. So time to use all the force components. First, we're given the fx, some of those. Okay, we have only x component that we have is xg x plus the xg of the y. Okay, sorry, xg of the yg of x, of course, yg of the x, like that. Then thinking about the direction here, this is moving to the right, moving to the left. I can just put that the xg to be negative. Goes like this. Then what you see there is minus xg cos 25 plus yg cos 25. That's equals to 0. 45. Sorry, 45. Yep, it gives you that. Yg cos 45 is exactly the same as xg cos 25, like this. You can cancel out the g's together. Then you get the relation between y and x, or like y is equals to, let's leave that. Y cos 45 is therefore x cos 25. Equation 1 from the fx. Okay, let's continue on the net force. So the y, which is equals to 0 again too. Add up all the values that you have. You're given that all that xgy plus ygy, I should say ygy. That plus that to the mg, so 15 times the g. So give that in the all, so that should be the negative minus 15g, sorry I missed that the direction. So we get xg sine 25 plus that yg sine 45 plus or minus 15g gives you 0. Then what you can do, you can cancel out all the g values like this. As a result of that, you get this. You get x sine 25 plus y sine 45 is equals to 15 then. Okay, well, let's solve that simultaneous equation then. We have two equations that are given for x and y. What do we do? You can either make the subject to the x and y from here, from 1, equation 1, from 1, y is then equals to x cos 25 divided by cos 45. Okay, and you can make equation 3. You can substitute the 3 into 1. Okay, that makes what? It's going in there, then x sine 25 plus that y is equals to x cos 25 on cos 45 times the sine 45 gives you 15 like this. Now you can use a calculator to find the exact sum of the values. So sine 25 gives you 0.422, so 0.422x to 3x, 0.423x plus, from that, cos 25 divided by cos 45, cos 25 and cos 45 times the sine 45, you'll get 0.906x is equals to 15 like this. Adding these two up, you can find the x finally, then plus the 0.423, you get 1.3293x is that equals to 15, therefore x is 15 divided by that value, you get 11.3 kg for the mass of the x. Once you get up to the x, then you can find the y from that, substitute back. Then y must be 11.3 times cos 25 divided by cos 45. That times cos 25 divided by cos 45, you get 14.5 kg then. This is the final answer then. Yep, I know, wow, so many x and y's, like, wow, g's and values too, but that's how you can deal with those values too. The good point is, I canceled out the g, so that you don't have to deal with the 9 point anymore too. Okay, it's kind of simplifying your equations into that, so they can find the x and y value separately. Oh,
Wait,
yes.
Can you explain the pulley again after the beginning?
The pulley.
Yeah.
Okay, pulley have an exciting up. Okay, before we put the force onto the wire, it doesn't have any force, but like you have to start from the linear forces first of all. When pulley, before we put the pulley, mass is hanged like this, exerting the forces. You have to understand that there are two types of forces applied now and in here. That one is this is moving downwards, okay, and pushing it upwards too. So on the side over here, you would actually sense that it's pulling down. So therefore, you're kind of exerting the opposite tension force, which is pulling up. Okay, the amount of the weight you can feel is the same as the amount of force they're putting up to. That's exactly the same amount of that too. So what that meant is the tension force, it's a good question by the way, tension forces is the same direction, or like they are having two directions. Depends on the perspective. In other words, giving you a situation there again, that we have a hanging mass, say that, we have a hanging mass is hanged, okay? The weight force mg is applied, so there will be a tension force T is applied from that side, okay?
Is T on the line?
T on the line, tension, it always exists in the tension there. But on the same side, the ceiling there will be equal amount of tension forces pulling this one down. Okay, again, this is known as Newton's third law, action and the reaction force. The equal amount of forces applied from the ceiling, but in the opposite direction. Does it make sense? Okay, so we generally say, well, we have two tension forces exist at the same time, so that is maintaining that, the tension between two. Okay, now change that to the pulley. Pulley is simply the tool that changes the direction of the forces. So instead of using that ceiling, if you hang that at the pulley like this. Oops. Okay. Always get fails. All right, that's better. No, maybe not. Okay, you see that pulley is something that helping you to change the direction of forces. That I'm now, instead of doing the vertical forces, I'm changing the horizontal force. So amount of force that I'm pulling this is exactly the same as the amount of force they hanged as well too. That's kind of easy to understand. But in terms of direction here, that I'm pulling towards to on your left. Can you see that? Okay, so that I can maintain, I can have the static equilibrium situations. But that means that I can actually feel that push forces are pulling, the tension is pulling to the right hand side. So there will be two types of tension forces exist too. On my hand's perspective, it will move to the right. On the mass's perspective, it will going upwards. Okay, same as this. This is pulling up. This side over here is pulling upwards, so they can maintain the positions too. And the side, in my perspective, is pulling down. Does it make sense? Okay, so same in here. If you apply the pulley, then you can imagine that. Oh, okay. Oh, it's not gonna fail. That. Okay, in here like this, that means there's a force pulling down, tension force pulling up, going up on the perspective of the base, and here it's going to the right on my perspective of the my hand. Same as that situations. And this is the reason why I set up the yes, there will be a tension force applied from a different axis perspective that's going upwards, but in this perspective is going the opposite direction, which is going that direction. But there will be, it will be simply like a force of the action. This is the action, that will be the reaction force.
So if it's pulling down,
yeah,
then you go YG, so is the G like minus 9.8?
Which one? The G?
Yeah.
For the case of that, yeah, it would be the matter of the direction too, so that's YG. The mass of that is in the minus YG. The tension force is then, they're known as the YG. Because they're moving in the opposite direction. Make sense?
Yeah.
Yep. So again, using that equilibrium, they're maintaining that static equilibrium. So adding these two up, cancel out. So you see the maintain tension, it's important to maintain the tension force to reach that static equilibrium. Yeah? Okay, or method. Simply think about it here. In this perspective, in the joint perspective here, to be able to make into static equilibrium, if one is pushing it down, okay, we can't have the force that pushing down here like this, can we? To reach the equilibrium. It's simply giving you that, oh, okay, something is pushing it down, means we need to have a force that's pushing up so that we can have the equilibrium state. This is probably the best way to understand the situations. So using like an imagination or using some like some real day examples too. Oh, yeah, they're in the equilibrium, so something pushing down, I must push it up. As simple as that. Okay. If you try to memorize that tension forces always be opposite, you get tripped over in the certain, especially in the exam. If you're like, oh, like okay, we learned that the tension force is always 2. It's kind of opposite to. Let's not go over that. Try to understand the diagram or understand the situation that we have a force that's pulling down, okay? And this is at the equilibrium, means that there must be forces that are pushing up.
So in the pulley question, we don't really find the tension. We find like we don't find the tension of the ropes, but we just like I don't know how to explain it.
Say it again. Sorry. We don't find what?
In the pulley question.
Yep.
Like, you know how in other questions we find tensions in the rope? Like in a pulley question, do we find tensions at all, or is it?
It's not about like a tension. The tension force, whether we measure the tension on here and there, they have an equal magnitude. So it doesn't matter like where you find the tension from here or there. Okay, so it's gotta be the tension on the rope always. Think about when we use the tension. Tension only exists when you have the tensile forces in the wire or like in the rope. For example, now this doesn't have any tension force because there's no forces that pulling. This is now tension. This is kind of tense. Does it make sense? Okay.
Yeah.
So you may think like ignoring the mass there. Maybe you can think about I'm exerting tension force. Okay, I pull it harder. But it seems like there's no change in here because I'm simply holding the greater force on my left hand too. See? No? Okay, another type of question that you get that you related to pulley, something that we love to put in the exam. Bit of like Newton's law too. There's something look like this. You'll probably see that a lot. We have pulley installed. We have 2 masses. Say M1 and M2 going like this. Okay, this is part of the chapter 2, a little bit of that. You can copy that down or like in terms of pulley. I explained that after break, by the way. Again, let's not go there. It's too complicated for now. Instead, let's do this. We have a inclined plane, to give you a hint for this, and we have a box on the inclined plane. After this, let's have a break. We have something that an inclined plane, and this assume that this is now at the static equilibrium. Static equilibrium. Okay. Where's my black? Okay. The things you have to do here is, yes, you still need to find it out what are the forces applied in there too. So think about the forces that we have. The mg, always from the center of the mass, pulling it down, it's perpendicular. Now, what are the forces? What are the other forces that are applied in here?
Isn't it the force sliding down?
That's sliding down. I mean, like it is what I mean by, think about like a real day example. You place something on the slope, then obviously they're kind of sliding down. I mean, if this is stationary, and if they are like in a static equilibrium, there must be a force that's holding all that together. My question is then, what are those forces here? Okay, first, think about the motion. If this is not really accelerating down, we would think, oh, yeah, okay, that force is a 0,2. Simple as that, okay, for the incline. Then, what are the forces applied in here? We have a normal reaction force, which is going upward like this. The normal means what? Always be perpendicular to the surface you're given. Anything else? Any other forces given here? Christine? Friction force. What would be the direction of friction force?
The opposite way it's going.
Going up or down?
If it's coming down, it's going up.
Yes. Think about the real example too. They want to come down. There's something that holds that in the station position would be the friction force, which is moving opposite direction, which is this direction here. This is the friction force there. Does it make sense? Okay. Then what makes them to make it slide? Is the weight. The weight, because of the weight, is kind of pushing down. Now, you may think that then should I? And if they give, let's give the angle theta here. Should we think that there's like two verticals? Yeah, as you can see, like a force diagram too. Now, I tell you a trick. Remember this. When you have an incline or decline, I can redraw the diagram like this. Instead of dealing with this plane, kind of inclined plane, I make it into the surface, the horizontal surface there. And that means we have tilted a little bit. Then you'll see that we have a force and the mass is kind of on the plane surface that has the normal reaction force going up, that has the friction force moving to this direction. I'm just following that diagram here. And also has, but it has the wave forces going into this direction like this. So what I did is I kinda rotated a little bit. But guess what? Instead of dealing with the two diagonal vectors in the first diagram here, I only need to deal with one. Yeah, because I have now vertical and horizontal vectors. Does it make sense? Now, as soon as you see like, we have a vertical or we have a diagonal vector, you may think, then I can draw the right angle triangle like this, instead of drawing the two right angle triangles. Does it make sense? Okay. Then what would be this angle? This angle is exactly same as the incline or decline of angle 2, that angle. The easiest way to think about it is, assume that you have a pole. Okay, this is my mirror, by the way, pipette. Pole that, if you're on the incline, okay, it's following that angle that you make incline or decline in your normal too, okay? I know this feels stupid, like it looks stupid, but that's probably the best way to, okay, if you're going there horizontally moving incline, yeah, then making exactly the same angle from that. Does it make sense? So always remember that the angle from the incline, decline is exactly same as angle made from that point, the vertical line to the mg goes like this. Easy, okay? Once you get it up to this stage here, we do the same thing. That this is mgx from this right angle triangles. You can find the mg sine theta. That'll be same as mg cos theta. The reason why I'm not providing you any formula, the value is because it's kind of generalized formula, something you have to understand, something you need to memorize it. Okay? It comes as mg sine theta, mg cos theta. Now, think about what we have. This is a static equilibrium still. That means that the sum of the fx would be 0, and sum of the fy also be 0 too. How to find the sum of the fx? We have mg sine theta and f, the friction force, as our what? The horizontal components. Where the friction force is moving to the positive direction, mg is going to this direction too. Just taking the direction right, that means ff minus that mg sine theta. For the vertical sections there, you would say what? This is showed that R, which is a normal reaction force. Remember that the normal reaction force is not same as the mg for the incline decline. We can only say when they're on this plane, this is the case mg equals to R. Not that. Okay? That's someone like told me like, isn't that always the same? No. Depends on your perspective, depends on the situation too. So that R is then equals to plus that minus mg cos theta here like this. Now R gives you this, mg cos theta from that. Yep. Good, okay. From the equation 1, guys, what was the friction force again? How do you find the friction force? Is equals to the coefficient of friction, mu times the R. So from 1, let's make it 2. From 1, what we can do, 0 is equals to mu times the normal reaction force, that's the definition of the friction force again, minus mg sine theta, like this. All right, then what you can do, you can substitute 2 into that, then you'll get mu times mg cos theta minus mg sine theta is equals to 0. Can you see that? Oh, now I can cancel mg together. Then mu would be same as what? Sine theta, move that, divided by cos theta. Oh, what's a mu? What's the sine divided by cos? That's a tan theta. So kind of proving that, oh, mu, if you have questions about finding the coefficient friction, the friction coefficient in this incline decline, this is how you find the mu value, the tan theta. Does it make sense to all? Okay, so how to find this one too. Have a think about it here. From this, R is equals to mg cos theta, guys. Okay, I want you to think about the situation that you're in the downhills. Okay, do you feel the same heaviness, same weight when you're moving down? Think about you climbing up or climbing down. Okay, when you're climbing down or coming down, you're able to jumping like moving really fast because you're going down, because your weight is helping you to move downwards too. Does it make sense? So in the fact is you actually feel lighter. Okay, mathematically in physics we can prove that your mass is calculated by mg. But because you're in the decline, we're moving downwards, it's same as the cos theta, mg of cos theta. Now, what's the cos theta value? Unless that's a 0, unless there's a cos 0 is equals to what? 1. Okay, remember that cos 0 equals to 1. Okay, unless you're in the plane, okay, if you're below that and as you increase the angle, you actually feel the less mg value on your bodies too. Does it make sense? This is called like an apparent weight. Apparently at the situation in the downhills, you feel lighter. Can you imagine those? Okay, you actually feel lighter as you're going down. So that's how we explain that your actual weight force can be varied in the different situations. Okay, it's not always same as the mg all the times. It can be varied, depends on your motions as well too. What about going up? That means you feel heavier because you feel like your weight is kind of pulling backwards. So you actually need to put more force to climb up. Is it harder, more working out? Is everyone done like this working out in the gym, that the climber, it's killer, okay? The reason is because always your weight force is kind of pulling you backwards too. So you actually feel much heavier than your normal body weight. Yeah, okay, you probably know what I mean. Like, if you ever run the uphills, and people hate to run the uphills because of that physics reasons too. Okay. Remember that, how to approach the question for the uphill and down. We'll come back to the uphill and downhills, moving up and down in chapter 2. This is a trick that we can use. Switch that, okay? Or you can draw that right angle triangle straight from here like this. Does it make sense to all? All right. Have a break. Is that better than last week, bud? No? No. How do I make this easy? Can I? No? Okay. I think there's a reason why people are dropping physics every year. Okay, the numbers are dropping.
Oh, this is the new calculator.
Pass that around. I like it. Did you get taller?
No, I got shorter.
Oh, I'm sorry. Did I say that last time too?
My doctor said I shrunk. Oh.
Really?
울지 마세요.
What? So I have this holiday course at Commitment. It's like stuff we already learned. But then it's 3 hours long. The maths, it's testing my English.
You know, I think I saw the Olivia once in the like the station. I think that was fun.
Olivia?
Like Olivia.
Olivia.
Like I was like, that's definitely her. But I didn't realize who it was. That was after they like spoke about the A1 thing. So I was like, what do I do? So she was so awkward.
How was it? It was really fun. I saw the video.
I only did one, but if you do multiple, it's not all. I think Leo and Jennifer were there. And I think they did like 3 or 4. So they would have had fun, but I was just, I only did one, so I just stayed there for like 8 hours going for like 6 minutes of stage time. But watching is fun.
Yeah, last night I was like searching for me. I was looking at the room when I was sitting down. I was looking at the code. Did you see me? I was like, I said it's 2:30.
The little commercial is fine. Look at that.
Did you get the river stuff? I feel like I still didn't even get it.
Sort of.
What's this one? Okay.
Dog.
Everyone in my friend group kind of hates her.
Why?
She, I don't know, like, her friend group her friend group is made out of people who got rejected from the OG
Oh.
Yeah. So it's like 4 people in a friend group, including her, right? And 2 of them, rejected from Livy's friend group. And 2 of them rejected from my friend group, so they formed their own friend group.
Are you and Lydia and
No, they were in different friend groups.
then how are you like this?
Cause she's like transfer, so like,
Olivia's transfer? Oh. From where?
God,
What's that?
it's like so far away.
Gordon.
No.
Is there a girl that made the stuff? This is what
But I know Amelissa. Is she Elizabeth?
You might know her in
Glasses?
No.
Oh.
Yes. Did she go to school?
That's not, her name's Alice.
Why is it Mr. Park? Mr. Park?
She like, I don't know, when she was like in year 8, she was obsessed with calling herself Alyssa.
What's her name again?
Alice.
Okay.
That was our reaction to me, like, what's the correlation? So she goes to school, right?
Yeah.
Okay. Okay. Okay.
So she has a formally changed her name. Principal calls herself.
Okay, let's start at chapter 2. Okay, so I will keep using that template that I gave you in the beginning of the class today. So first determine the motions and then find out all the force components. And after that, you can think of it like, other forces that. All right, page 34. So this is what I just explained to you about analyzing vectors, forces. And page 35 shows you that's what I mean by going uphill and downhills. As you can see from that, figure 1 and 2, you see they're going downhills. We're taking down the weight force going downwards there. So considering that the weight force is having the two components, up and down. Okay, instead of dealing with the two diagonal vectors, just deal with one. That's actually a pretty easy one to do it. So same for the going uphills, it's good, uphills, that would be, driving uphill would be the same thing. So that's driving uphills. So let's have a look at the question 2.2, page 36. Question 1, a car of mass 1600 kilo left to park on the steep but rough road begins to roll down into the hill. After a short while, it reaches a constant speed. The road is inclined at 15 degrees to the horizontals. Its speed is sufficiently slow that air resistance is insignificant and it can be ignored. Determine the magnitude of the road friction on the car while it is rolling at constant speed. Okay, let's draw the diagram for this. We have a steep 15 degrees downhills. A car is going downwards there. Now remember that this is moving down with a constant velocity. Okay. First, let's determine the motion. The car is moving in constant velocity. So Matthew, what does it mean by constant velocity in terms of the net force there?
It would be 0.
It would be 0 too, because there is no change in motion. This is not at the static equilibrium, but simply mean we have the 0 force applied there. Does it make sense? After you realize that, you need to show all the force component applied on the car. So always start with the weight force from the center. That's the weight force, mg, is pushing it down. There will be normal reaction force perpendicular to the surface. Friction force will be applied going opposite direction. And there will be a driving force that's pushing it down. Does it make sense? Okay, so driving force, F, that's a driving force, because due to that. Oh, sorry, it's not a driving force, it's not really driving, it's basically having that forces only. Sorry, my bad. Let's have 3 forces there all together. Once you analyze the forces, then identify any diagonal vectors. Remember that in the uphill and downhills, we're taking this weight force as the diagonal vector. So showing that it has 2 components going down and forwards. That is mg. So from that 15 degrees here, you can just write straight down. That'll be mg cos 15. That'll be mg sine 15 like this. All right. I do the exactly same thing. So let's add it up all the forces. The force on y, then adding up that is equals to, we have mg. Let's write it down. R plus minus mg cos 15. That's giving you what? Equals to 0. Does it make sense? Okay. And you can break the subject to R. That is mg cos 15. Equation 1. Net force on x can also be found in the same manner, that we're adding all the force components that we have. What we have now is with mg sine 15 moving to the forward minus that, the ff, or the mu r, because the friction force is now equals to the mu times the r. This gives you that 0 in the net, again, because that net force is 0. Not a static equilibrium, because it's moving in constant velocity. Remember that. We kind of discussed it quite a lot of times. Then mu r will give you mg sine 15, given here, let that 2, equation 2. Then what you can do, you can substitute the 1 into 2 there. Now you're to get mg, mu times mg cos 15 would be equals to mg sine 15. See that cancel out the mg's together, okay, or g's as well too. Then you to get mu is equals to sine 15 divided by cos 15, give you 10 15 as a result of that. So 10 15 is simply giving you 0.2679, given the coefficient friction of rod frictions. So if that's this, okay, let's find R then. R is equals to mg cos theta, so that's the m 1600 times that 9.8 times cos 15. Therefore, friction force, which is same as a mu r, is that times 0.2679 times 1600 times 9.8 times cos 15. You can find that before better. That times 1600 times 9.8 times cos 15. You must get 4,058 newtons. Given that suffix of 2, this is same as 4,100 newtons then. This is a friction force. Again, if you understood like how to find the horizontal vertical vectors or from diagonal vectors, that's pretty straightforward, I should say, okay? But if you don't really understand what I mean by net force is 0, then yeah, you can't actually solve the question. So this is why you need to determine the motions, therefore find it out the net force values initially, and then solve the question from them. Question 2. 15 kilo mass is in static equilibrium on a 6 degrees incline. What is the minimum bail for the friction force between the mass and this value, sorry, that should be value, for the frictional force between the mass and the surface. Again, let's draw out all the force components given that. We have given a weight force pushing it down, mg. Okay, there will be a normal reaction force pushing it up. Okay, then we also have downhills, the friction force moving into this direction, friction force going in here like this, along with the incline, by the way. Make sense? Okay, then you can draw out the force component of those. It's a really small triangle, so you get this and that. That's a 6 degrees. Then we have mg cos 6 and mg sine 6 degrees here like this. It'll be the exactly same working out, so let's write it down in question 2 on here. Question 2. Now, it's at the static equilibrium, so you can start like, okay, that means gives us a net force to be 0 all the way. After you get that, you can get the net force x is therefore be 0. Okay, on x-axis we only have the friction force, which is moving backwards. Plus that too, we have the mg sine 6 gives us that 15 kilos is given to. Net force on y is a 0 again too, so we have r plus minus mg cos 6 like this too. Gives us that r is equals to mg times cos 6. Okay, so equation 1, equation 2, what you can do, you can substitute 2 into the 1. Then you get friction force is equals to mg sine 6. Actually, we don't really need to, just need to find the friction force. Okay, that's it. M stands for the 15 times 9.8 times sine 6. We didn't really need to do that, so don't worry about this process there. Then you get 15 times 9.8 times sine 6. Then you get 15.4 newtons. That's the amount of the friction force that needs to be applied. Too easy for the incline, decline. I mean, it's just the force diagram again too. Okay. Let's do 3. 50 kilo block sits on the ramp, which is inclined at 25 degrees, 25 degrees, as shown in the diagram. So the ramp applies a frictional force of the 0.2 newtons per kilo. Okay, that's giving you as newtons per kilo. So have a think about the 0.2 newtons per kilo there. Okay, this is not a actual force yet. Okay, this is like something that apply from that, what? From the kilograms too. So the actual amount of friction force, this should be calculated by 0.2 newtons per kg. That times that the force of the weight of that mass, which is a 50. So this will give you now times that 10 newtons. 10 newtons would be like an actual value of the friction force that applied. How do I know that from that? I read the unit, newtons per kilo. Newtons per kilo stands for like per kilogram it applies that much of the force of newtons. So this is how we use that the units to determine that whether that's not a force or like a different unit. Okay, or that's actually the same as the coefficient value, mu. All right, then draw the label on the diagram on all the forces that are acting on the 50 kilo block. Let's zoom in a little bit. I can use that. We have first showing that mg, pulling it down. We have a normal reaction force pushing this up, okay? And then incline at 25 and applies friction force. We don't know whether that's the net force to be 0 yet, so let's find it out. It's given from the question B. There will be a friction force that's applied on this side over here like this. Okay, from the mg we can just draw that two force components at 25 degrees. So mg cos 25 and mg sine 25. Running out of space. Mg sine 25, that in the right angle triangle. Remember that this is not giving you that the static equilibrium. We don't know whether it's moving or down. Okay, so we have to think about the net forces later on too. They're slightly twisted questions. A done. B, let's find that. Calculate the net force on the acceleration acting on the block. So what we have to do, we're gonna find the Fx and Fy sum individually. So Fx, what we have, we're mg sine 25, that plus that the frictional force, but in this case moving in the opposite direction. Now, can we find the Fx value? You can, because we know that 50 times 9.8 times sine 25 minus that, we found the 10 newtons initially. So put that in your calculator, that 50 times 9.8 times sine 25 and minus 10. Ooh, actually, that's giving you quite a lot of value. 197 newtons is actually moving forward. Okay, let's do the same with Fy. That we have the normal reaction force, and that no, in fact it would be 0. How do I know that that force on the y would be 0? How do we know that? Thinking about the meaning of when the net force y is not 0, we have some vertical forces applied. It means that it's either the 50 kilos moving up or the down. Okay, I'm not talking about on the plane. So on the plane here like this, when it's moving up, it means someone actually lift it up. When moving down, means someone kind of push that into that block. So we don't have that because it's kind of going along with the plane. This is why we can make the Fy to be 0 all the way. Does it make sense? Okay, this is how we use the motion to determine the net force again. Okay, Ewan? Okay, then this is the only force that applied, the net force applied on that. So therefore, net force is equals to the amount of force applied on X, that's 197 newtons. Yep, and then what else? We know that the angle's at 25 degrees moving down. So therefore, and the question asks you to find the acceleration. Time to use then finally MA. How to find the A? A is then equals to F on M, that's 197 divided by 50. So that divided by 50, that gives you 3.94 meters per second squared at the 25 degrees, 25 degrees down the hills. Shall we interpret that again? 3.94 meters per second squared means what? It's changing its velocity by 3.94 meters per second in every second. It's getting faster, like a snowball. It's getting faster as it's going down, due to that small amount of the friction force applied there. That's what happened to you when you go like when you're skiing. By the way, going down hills and the skiing, like getting accelerated, you get more force on you from your weight. Okay, not from like something else. No one's pushing you back. We don't do that. Okay, your weight is basically what you're making it going faster in that case, and combination with some friction force. Okay, let's skip 4. Can you do 5, please? Can you try for 5? Give you about 5 minutes. That's meters per second squared. That -2. So now we're talking about something like not at the static equilibrium. So have a think about what that means in here. Okay, so I can redraw that. Okay, or I can use the diagram given here to draw the forces applied in here. Or you may just think that as that plane with inclined plane is just a plane like this, instead of kind of horizontal plane, then you may think like, oh, mg has the two components of the x and y. So that's mg, that's giving you that 25 degrees there. So you can go straight. Mg sine 25 and mg cos 25 from that perspective. The t has also two components. There's 1 and 2 with the 20 degrees given here. It's a given on the plane. From the plane, remember that along with the plane. Then that angle here, the t cos 20 and t sine 20 here like this. Again, I'm just dealing with the whatever values you were given. And remember that this is not a situation of the static equilibrium. We don't know. It's not given. Then the net force is not the 0. And the question is actually asking you to find the net force value. So how do we do that? We got to find the individual x and y components adding up together. So for the x-axis, okay, one more thing. It's giving you that, the smooth ramp. This is actually kind of another way we can describe that as there is no friction force. Or the frictionless. So what we can do, we can ignore that friction force from that vector diagram there. Okay, and this makes your work easier by doing so. So net force on the x-axis, then we only have a two component. One is t cos 20, and we have the mg plus minus mg sine 25. Okay, can we solve that? We know what the mg, so we can find actually what the t is from here. So let's do that actually. No, we can't. This is okay. This is not equals to 0. It's something that different to like the previous question. We don't know because it's still moving. We don't know whether it's 0 or not. So we can't just make it to 0. Don't use that. This is why you need to understand the motion. You need to understand the question. Net force on y is then equals to. Now this is the thing. But in an incline or decline, as long as they're intact on the surface, I can tell this is 0 but. Does it make sense? It's moving along with the horizontal axis, but it's not really moving up nor down. So we can make that to be 0. Now adding all the components that we have, first we have the normal reaction force R, that plus we have mg cos 25, which is moving down, so I'm going to put the negative, minus plus t sine 20 here like this. Okay, so this gives you that mg cos 25 is equals to all the values that you're given. And oh, actually, sorry, I forgot to mention that. We don't know what acceleration, what force is, but we just give it that. The block is pulled at a ramp at acceleration 0.25 meters per 0. meters per second given over here. Means that the acceleration, net acceleration applied to that is already given as 0.25 meters per second squared. Kind of missed that. Okay, from that you can use Newton's second law if you want to. The net force is simply ma. It can be written as 250 times that 0.25, which gives you 250 times 0.25, giving you 62.5 newtons in the angle, along with the at 25 degrees along with the slope. I mean, that's the answer for A actually. Okay, and then I can continue on from this point in here for the B. Okay, so we now got the net force is applied 62.5 newtons is a net force. And we got to find this values over here, that's from the tension force. Okay, question B. Let's do question by questions. What is the component of the wave force is the block acting down the incline? So let's do that. We have a x component. is known as mg sine 25. That is, given the mass of that 250 times sine 25, then 250 times 9.8 times sine 25, you would get 1035 newtons. Okay, and that's going downhills. Y components would be mg cos 25, that's a 250, 9.8 times cos 25 again too, so 250 times 9.8 times cos 25, you would get 2220 newtons. Vertically down. That's a down, and to the left in case of this. Okay, that's for B. For C then, find the tension force from it. Okay, good to remember this. The net force, if you have a net force of that, let's draw that. Net force is known as 62.5 newtons. That's a net force, along with the axis of the 25 degrees there. Okay, now what I see from the net force is this is the diagonal vector. This means it would have the component x and y here again too. That component x is simply x, and the y. I do the exactly same thing for the diagonal vectors. But you see that, oh, but did we found that from here? We did. Then we found that from there, we kind of did. Okay, so this is how you can use that force diagram and use the formulas to figure out. So for Fx, from that right angle triangle, what you can tell is same as 62.5 times cos 25. It's actually given. Okay, you can find Fy, that's the same as 62.5 times sine 25 from the right angle triangle too. Now we found it out from the Fx is equals to this value there. Okay, so this Fx is therefore t cos 20 minus. You may use the exact value that we found, mg sine 25, from that minus 1035 from question B. This is equals to 62.5 Fx cos 25 like this. Does it make sense? Then we can easily find the t value from here. 62.5 cos 25 plus 1035 divided by cos 20 will give you the t value then. As the question I can find the tension force, so 62.5 times cos 25 plus 1035 and divided by cos 20, you will get 1161 newtons for the tension force. Okay, question didn't ask you to find the magnitude. I mean, you need to show the direction as well too. So this is tension force at if that's a 20, okay, guys, think about it. It's a 20 and 25, which means it's actually inclining in 45 altogether. Does it make sense? Okay, so you have to set at 45 degrees from the horizontal. Or you may say 20 degrees above that 25 degrees incline. That's the same thing, the 45 degrees too. Okay. Okay. Any questions about this? Question 5? Okay. So I kind of introduced what the Newton's second law is. Yes, you probably know like F equals to ma from the year 10, year 9. Simply, the force is the same as the sum of the product of the mass and the acceleration. But do not put yourself into the F equals ma. That's a kind of trap. I always call it a trap because it's out of 10 people. Like whenever I ask them about, hey, can you tell me what the force is? They 10 out of 10 they say, oh, it's ma. Okay, it's not all of that. You always remember back to when there's a force applied, it's always about the change in motions. Okay, it's a push that while you're running, if someone pushes you, that's the push I'm talking about, making you getting faster or change the motions to, or make you to stop. Okay, the reason why I brought that is just like what I've used in the previous question, that the net force, you can just write that in here too. Then this means net force is equals to net times ma here like this too. This is kind of hidden definition of the F equals to ma from the net force. Okay, Or you may think like a net force on X means net force on M, X times AX here as well too. Or simply, we can't change the mass, this is the same as net force M times the net force on the AX here as well too. In other words, we are able to find that, just like we found the two components of the the diagonal vectors, we are able to find that individual horizontal acceleration, individual horizontal vertical acceleration, kind of like separately too. Now, meaning of this, it has many meaning implied that too. This means that it's either be sum of the m times the sum of the acceleration too. Okay, remember this. So for example, I'll give you one example. Okay, I have a box, two boxes. Say I have the 10 kilo and the 5 kg. Okay, I push that with say a force of the 100 newtons. You'll probably get questions like these quite a lot from now on too. Okay, if I push that. Okay, the way we can think about the question is that, oh, okay, both of the 10 and 5 now receive that 100 newtons. And you have to understand that, oh, the net force is net MA, isn't it? Okay, that means sum of the masses times the sum of the acceleration. And we apply to both of them too. Or net acceleration, because imagine that if you push that 10 and 5 kilo, which is intact, both of the 10 and 5 will move in the same motion. In other words, they'll have the same acceleration applied to too. So that's how we can apply that. This is a 10 plus 5 times that acceleration. That gives you, therefore, acceleration net. Acceleration applied on both of them will be the same as the 10 plus 5. So 100 divided by 15 gives you 6.67 meters per second squared on both of them. Okay, that's what I mean by, you got to think about the sum of the masses for the F equals to MA. Does it make sense to you? Okay, it's not that complicated for the net, because we've been talking about net forces quite a lot, so it's not hard to understand about net acceleration too. So have a look at the question 2.2. A 65 kilo physics teacher, I'm not, okay, starting from rest, glides gracefully, I don't know who's that, okay, goes gracefully down a slide in the local playground. The net force on her during the slide is constant 350 newtons. How long will it take her to reach the bottom of the 8-meter slide? Why are we getting that question? Interesting. Can you see that we get questions from like module 1, the motion equations now? Okay. Later on, we're going to learn about energies too. You can solve the same question, the energy contest too, but let's focus on the motion equations. So A, let's down the slide. So we're giving that 350. So the net force applied on the teacher is 350 Newton. That's given. And this is the same as the net MA. Now in here, the mass is just the one mass, which is the mass of the teacher, which is 65 kilo. Therefore, acceleration applied to her is F on M, or net on that is a 350. Net acceleration is same as that, 350 divided by 65, which gives you 5. Let's try again. Losing that, 5.34, 5.38 meter per second squared. This is the amount of the acceleration she's receiving now. Okay, now let's write it down, all the relevant information you're given. You're given that, the constant 50, and we have the slide bottom of that, the S is given as 8.0 meter down. So she's moving downwards, by the way, because sliding down. Okay, what's initial speed? Initially, she was at rest, giving you that 0. All right, we have S and U, and we have an acceleration. The question is asking you the time. What do we do? S is equals to ut plus half at squared. Yes, I ask you to memorize that. Time to use this. Okay, then S is giving you that, I had to take the minus 8.0. We can just post you the plus, that doesn't really matter for this, but let's follow that. Minus half times 5.38 times the t squared here like this. Then t, you see that cancel out the minus there. So 8 times 2 and divided by 5.38 and square root of that, you're going to get 1.772 seconds to slide down the slope. Okay, why are we counting with the weight forces here? I mean, like the teacher must have some weight force, but why am I not really considering about weight force at all? Well, why am I not even trying to show the diagram? Any idea, you mean? No? Look into the net force. Net force. It means that it implies that it's already having included the weight forces inside of that too. So once you get a net force value, it means it's included that weight force and a friction force and normal reaction force inside of that. Does it make sense? Okay. So if you're not given the net force, then you may need to do some other process of the downhills, find the net force values too, and get the same answer like that. So do not add up extra forces once you get a net force. It's given. It's a given for you. All right, 2. When the head of the 80 kilo bungee jumper is 24 meters from the surface of the water below, her velocity is 60 meters per second downward, and the tension in the bungee cord is 1200 newtons. Air resistance can be assumed to be negligible. Okay, what is her acceleration at that instant? Okay, let's do that question 2A. Let's draw the diagram there. 24 meters from the water below is 80 kilo bungee jumper, so she's falling down. I think hangman might look like this. That's water, that too. Guys, you don't have to draw the fancy diagram, by the way. That's enough, okay, to understand what's going on. She's falling down, bungee jumping, by the way, okay. All right, we have a 24 meters that from the surface of the water below. Oh, sorry, the head is actually 24 meters, so that's at 24 meters now, quite high. And she's 80 kilo, and her velocity now, she's now falling in the velocity u, I take it at 16 meters per second, like this. Okay, so she's now falling down. Okay, let's see. Hey, the tension force, however, exists. We have a tension force T was given as 1200 newtons there. Okay, I really recommend you to draw any sort of diagram. Okay, it could be better. It must be better than mine, by the way, too, because to understand the question, to show all the relevant information, and guess what? This will save you time quite a lot. That you don't have to read the question back, because it has all the information you needed. All right. Hey, what is her acceleration at that instant? All right, let's think about what forces are applied on her now. Doesn't really matter if she's in the free fall or not. She's still having some weight force. That's her pulling her down. At the same time, she has tension force holding her up at 1200. Does it make sense? Okay. So can we think like there's no horizontal forces whatsoever applied to her? So we have to think about this here. The net force applied to her is now be weight force, which is a minus mg, that's pulling her down or pushing her down, and 1200 newton that's pushing her up. All right, the mg can be found from the kilo, so minus 80 times 9.8 plus 1200, and you get the net force value, that is 80 times 9.8 and 1200. You get 416 newtons. That'll be up. Yep, okay. That's what? Same as the MA. Then net acceleration now applied on her is the net force divided by the m value. So 416 divided by m, which is again of 80 kilomans. So you'll get 5.2 meters per second. Direction upwards. So she's now in this point of like she's kind of straight, kind of pushed upwards due to the tension force of bungee jumper rope. Okay, so therefore she's not really free falling. She's not jumping into the water. Maybe she's safe. Let's find out. Question B: if her acceleration remain the same, will she stop before the water or not? Or will she get wet or not? Okay, it'll be funny like if she get wet. Let's say B. Let's write it down all the relevant information that you're given. That you know that you need, at the speed at the instant that she's falling down, it's given as 16 meters per second. Let's give it. The displacement. Okay, I need to take the negative here because she's falling downwards too. Let's consider about the direction too. Now she's falling downwards means that her displacement would be minus 24 meters per meter going down here too. Okay, important to keep the direction right, negative and negative. Okay, acceleration, we found that that's a positive 5.2 meters per second squared because they are upward acceleration applied. Then time to find that, no, actually minus 24 is the surface of the water. Okay, now think about here. When she stopped at the bottom, can we say the velocity is 0? Okay, due to the bungee jumping here. So let's ignore the s value because we want to determine that whether s will be greater or less than the s. So I'm going to take these values over here. Then once you get the combination of u and a and v, you can think about the motion equation. V squared equals to u squared plus 2as here like this. Then 0 is equals to u minus 16 squared minus plus that 2as, 2 times 5.2 times s here like this. That s, you need to get an s in the negative value because you're falling down. So 16 squared divided by 2 times 5.2, the negative of that. So 16 squared divided by 2 and 5.2. Oh. You should get 24.06 meter down. So what that means is her head, 60 centimeters of her head to here, we're gonna pretty much go into the water. She's gonna get wet in this case. This is greater than 24 meters, the height. So therefore, she will get wet. 60 centimeters will be just probably the length of the up to the chest, probably. Okay, it's not a nice feeling. But that's how you can calculate the values too. Can you see, like, spot the difference between like what we practiced last week and today, the half of that, and this question here? I'm giving you a situation that when the net force is not 0 anymore. Okay, so you must know the difference between two. Don't just assume that, oh, net force is 0. Think about meaning of the net force 0 in that situation here. That means is either she's stationary or she's falling in the constant speed. So, in fact, like in the reality, in the free fall situations, it doesn't happen. Okay, let's do one more. Actually, we got to do. There are more questions there. Let's continue from the question 3 next week. Do we do up to question 2? Yeah. So let's do from question 3, 4, 5 for the Newton's second law next week too. I give you some homeworks for the kind of related to Newton's law and incline, decline, a bit of like a static equilibrium if you can. What we're going to do next week, so in chapter 2, that is Newton's third law. You got to get the questions like this a lot, and I'm sorry, you will hate this. You're like, oh, no. You'll be. This is what you get. Every year, I'm sorry, James Bruce, every year your school's giving this question in your first assessment, poorly. Whether you like it or not, you will get it. Okay? So, it's in the workbook. Yeah. So you gotta get to some of the questions like this next week too. So, but I'm trying to use that what we did today again and again and again. The reason why I'm not giving you a topic test yet. Yeah, we have done few. We finished module 1. We're like doing the first 2 chapters of module 2. It's time to give you some topic test. But reason why I'm not giving you yet is I know you're not gonna make it. I know for now, because I intend to not to give the topic test till you feel more comfortable dealing with the forces. Okay, you'll be like when. It will be. Yeah, let's keep trying. So most likely after next week, we're gonna have a topic test of up to here, up to chapter 2, before we move on to the energy. I don't mean like I'm not gonna give you any topic tests. So it's gonna be probably when Damien comes back. So when everyone's here, I give you a topic test when the school starts. Is anyone going back to school on Tuesday or Wednesday next week, or everyone coming back on Thursday? I just want to have a double check because some kids, private schools going back on Tuesday. Teachers going back, and private schools going from this Thursday too. Sucks. All right, that's it. Okay. Homework. Can I collect the homework from last week and give you homework for this week too? It will be the chapter exercise, anyways.
Oh. It's like 3 Ashley's in there. Oh, yeah. Did she? I actually didn't know that. Now she did. Why? She didn't like it though. I wish I could. No, but I love her. She's actually quite an amusing person. I'm an amusing person. Yeah. I think it's like the strict teachers.
Don't forget your bread.
They like humbles every student.
Here you go. Okay. All right then. You have a good afternoon. Have a good rest of your holiday.